Hello everyone! Today I would like to have a chat about a problem that has haunted me for the last 10 years of my research. That is the correlation between caching, one of the most common optimization when programming, and the general idea of being able to write modularly correct code. And today I'm not going to give you any solution, I'm just going to raise some questions on how this is a problem. The connection of those two topics doesn't really work. So, what do we mean when we say that there is modularly correct code? Modularity is this general idea where you can have little islands of reasoning, little silos of information that can make sense in isolation. And then when you put them together, if they are individually correct, you get a correct result. In particular, we can make an example for this with a little timeline. We have that in 2018, Bob writes some correct code. And this is his own little silos, his little chunk of correct code. And this code have a contract. That is the way other unit of reasoning can talk with this correct code of Bob in 2018. And then in 2019, Alice writes another chunk of correct code. And this code depends from the original silos of Bob. And then in 2020, Bob updates his code, but keeps the same contract. That is, from the outside, the silos looks the same. And Bob can use the type system and testing to check his work, to verify if it's really keeping the same contract. And now we have two different outcomes here, We have a great smile success where in 2021 the code of Alice still works with no problem. And then we can have a non-critical failure scenario where something goes wrong, but Alice can discover the problem easily. In particular, Alice may have a good test suite for regression testing, and Alice can discover with tests that something doesn't work anymore. And so Alice can fix the problem. And ideally, Alice can identify what part of Bob code is giving the trouble, in which way Bob have broken his contract. And the second piece of our puzzle is caching. So caching is maybe the most common optimization in coding, in programming, and it's based on the idea that some computations can be expensive and that many of those expensive computations end up being repeated over and over again. And so if we just could save in a little space in the memory the information about the result of the computation, and if we had some way to return the result directly instead of having to do again all of this complex and long work, we will save a lot of time. And so caching is any kind of technique or pattern that let you recognize that a computation have already been executed and can get you to the result without actually recomputing the whole computation. And fundamentally, there is a big assumption. Reusing the cache or recomputing the value should produce the same result. Caching need to be unobservable, or if you prefer, need to be only observable in terms of performance. The behavior of the application should not change. Now let's make an example where we are doing code for a supermarket. And in the supermarket we have many items that we sell, and there are a lot of different discounts. And they can be quite complicated, and they can apply on top of each other in various different ways. And so in 2018, Bob writes a method, compute price, that takes an item and a map of discounts. And in the method, there is a lot of computation, and eventually we get a price. Now, in 2019, Alice uses compute price for the checkout operation. And she discovered that compute price is very slow. And moreover, the same items are processed over and over again. So some items are very popular, and so they got sold hundreds of times every day. And this looks like the perfect occasion to use caching. Now, Alice knows that caching can be dangerous. Caching needs to be done correctly. We need to make sure that if we were to recompute the value, they will recompute the operation, or if we just access the cached value, we should always get the same result. And so Alice writes a lot of tests to check that this is working properly. And also, Alice realized that if the map of discounts change, the compute price may, give a different result. That is, the cache needs to be invalidated whenever the map of discount is mutated. And that's fine, she handled this. She makes sure that every time there is a mutation in the map of discount, the cache is cleared. And for a while, for a long, beautiful while, everything works fine. One day, the boss sees that there is a lot of fruit that end up expiring on the shelf. And so the boss decides to apply a further discount. Items that are near the expire date need to be cheaper so that, they can go and they will not rot on the shelf. And so, in 2020, Bob edits the method compute price, and this new kind of discount is time sensitive. It's about the date of today and the expire date of the product. And so now the method compute price technically depends on the day you call it. And so now the cache invalidation strategy of Alice doesn't work anymore. Now we should invalidate the cache every day, in addition of just invalidating a cache when the discounts are modified. But all the tests of Alice still pass. And so no one noticed anything wrong. So how it can be possible that all the tests of Alice still pass? Well, she have wrote fantastic tests, but most test suites runs in a single day. And so they will all pass because the problem only happened between days. Now, this is an extreme situation, but in caching, it often happens that the event that breaks the cache, that requires the cache to be invalidated, is something quite alien, something quite difficult to consider in the scope of unit testing. And so, after a long time, a cashier noticed that the fresh bananas are still priced as the very old ones. And who knows for how long the system have not worked as intended. The boss is furious and ask for a code review because he wants to understand who is at fault here. But who is at fault? I mean, Bob wrote a good initial implementation. Alice uses the code of Bob as it was perfectly, and she also wrote a lot of great tests. The boss made a very reasonable request. Bob implemented the requested change correctly. And there was no way for Bob to know about Alice caching. And Alice had no way to know about the change. That is, the only way they could have known the problem is if they were talking continuously and discuss absolutely every detail of their code with each other. But that's not modular reasoning. That means that in order to write correct code, you need the global understanding over the whole system that for sizable systems is impossible. So, I think that here the programming language is at fault. But what programming language? I haven't said anything about the programming language, But basically, every programming language that I know of have those kind of problems. And so, I will say that caching is intrinsically non-modular and must be handled by the programming language and not directly by the programmer. Now, there is a beautiful citation that says there are only two hard things in computer science: caching validation and naming things. And here I'm trying to solve cache and caching invalidation. Now, next time I will introduce you 42, the new programming language that I've designed to solve caching, to make so that you can have modular reasoning and caching coexist without trouble. And one of the interesting things that I've discovered is that once you solve caching, you automatically solve a lot of other problems that are hunting programs all over the place. So in particular, I'm able to offer correct parallelism in addition of correct caching. So, see you next time, maybe in 1 week, to talk about the new 42 programming language.